Hello. Today, we're going to talk about our research in the area of power electronics interfacing with the power grid. In particular, we call it power electronics at the network edge, which is also acronymed as PON. This is a recently granted US patent, as you see here below. So the way we think about the future power systems, in particular, in the future power distribution systems, is that we can think of them as an architecture that couples many microgrids or nanogrids collectively. Each of these microgrids or nanogrids would have certain capability to function on their own, but also will be connecting with the power distribution systems through the interface, which is power electronically interfaced voltage source inverter type interfaces. So the idea of power electronic intelligence at the network edge really started from recognizing that power electronics has a great amount of potential to have much more autonomy and control at the edge of the grid. And because of that, there are a number of breakthrough innovations that could happen at the periphery of the grid. A number of applications include things like bidirectional power flow control, things like energy budgeting, things like fully decentralized control of voltage, and so on. And these are all enabled by such an architecture. And there are also very interesting dynamic improvements if we were to utilize this power electronically interfaced distribution grid to the best that it can. These days, there has been a popular term called grid forming inverters. And we have done some work that paved the way for some of these discussions back in 2015, which is essentially recognizing the fact that because of these power electronic interfaces, the control at such interface could be much more versatile compared to conventional synchronous generator controls. And because of that, we leapfrogged a traditional generation control from synchronous generator paradigm, which is largely based on frequency droop method, towards a new idea that is so-called phase angle, voltage angle droop control method at point of common coupling. So the idea is to develop the droop control from certain sensor capabilities such as synchrophasors or phasor measurement unit, and provide the direct feedback based on the angle difference between the measured angle and the reference angle. This is in direct contrast in a lot of existing work that is designing the frequency feedback or frequency droop, very much in the same line of thought of most synchronous generators. And the reason we proposed that was because when it comes to the analysis of large scale networked microgrid stabilities, these traditional frequency droop based methods are structurally a singular, and that gave a lot of challenges in quantifying regions of stability. Whereas in the context of this angle droop based method, one can actually design asymptotic stability in the large through this innovation at the architecture and control design level. And that provided a provable transient performances for asymptotic stability in the large if each of this interface is designed small enough of a droop. So that is for the first time that one can actually guarantee a large network stability of interconnected microgrid systems. And it truly is enabling opportunities and possibilities such as plug and play. And this is something to be noted as a difference between most of the frequency droop-based control method that are quite popularized these days by the notion of grid-forming inverters. And this could possibly be thought of as a grid-forming inverter of the next generation. And we have also tested out in some of these prototypes developed by our colleague, Professor Ingetti's labs. And because of that, it enables a number of different opportunities for applications. And you can refer to some other parts of the research sections on the potential of these applications in protection, in control, and dynamic security monitoring. Thank you for your attention.